Yes.
Coming back. So okay.
Okay. All right. Okay. Can you hear? Oh, I don't have a camera on this on this. This is my desktop. Okay. So I guess I can. Shall I start? Can you hear me? Hello.
Hello.
Can you hear me?
This is Alex. I can hear you, but I cannot hear Yusuf. So his microphone might be muted. But I can hear you, so I assume that the others can hear you, and I can see your screen. So it looks fine. So I think you should be able to go.
Yes, now you can hear me.
Yeah,
I was
my okay. All right. Yeah, so the I know my microphone is not muted. Okay. Anyway, what I'm going to be talking about mesh-free methods applied to partial and integral equations. And one of the things that I like about mesh-free methods is you don't need to try to get a mesh for problems. These are just scattered points, and they can be in any dimensional space. And this is especially important when you want to do in higher dimensional problems. Just think of how much I have worked with finite elements and making meshes, and it's a pain in the neck. You can spend weeks trying to get a good 3D mesh before you can even start the calculations. And here with mesh free, you can do it any dimensions you want as long as no 2 points coincide numerically. Okay, next slide. Next slide.
yes now.
Okay.
واضح عندنا مشكلة.
Better still. Hello. Okay, hello. Where are we?
Sometimes
Hello?
we experience some internet connection. So we are back. We are back.
Okay. Yes, I also have problems with internet connections sometimes too. All right. All right. Yeah. So you need better solvers and truncated singular value decomposition. Anyway, high precision arithmetic is, I think, very important, and variable shape parameters and front tracking. Front tracking is very easy to do with no meshes at all. So next slide, please. Next slide. Okay. So Professor Chang was talking about the H scheme, which is really mesh refinement, discretization refinement, and the C scheme, which is adjusting the multi-quadratic shape parameters to get the best combination. So you can do this for the PDEs and boundary conditions. So one thing is that the multi-quadratic and Gaussians are pre-wavelets. They are non-orthonormalized wavelet functions. So you have translators, X sub j, and you have dilators, which are the C sub j's, and these are also rotationally rotationally invariant. Okay, I guess we're kind of all right. Yes, and the beta exponent is important in influencing the shape of the basis function phi sub j. So this is one of the, some people like to use the assumption that this pre-wavelet shape parameter is uniformly constant. I never have done that. Anyway, the thing is, if you have the rows of the matrix to be as distinct as possible, you have better conditioning, and it's also better. But again, we have people who have their own viewpoints. Okay, I'm a troublemaker, never do anything according to plan. Okay, next slide, please. So Monich and Nelson showed that multi-quadric interpolation and its derivatives converge exponentially. So they go like lambda to the muth power, which is can be some large number, minus the absolute value of m, where m is the derivative. So if you use antiderivatives, this convergence rate increases faster. So higher order differentiation lessens the rate of convergence, and integration increases the rate of convergence. Next, please. So if you want the best accuracy with the minimum CPU time, you want this ratio of the shape parameter over the spacing to go to infinity. So one is the H scheme, in which you refine the distance, keeping the shape parameter fixed, and the C scheme means that you increase the shape parameter and you can use a coarse distance spacing. So basically, the C scheme is ideal and most efficient. However, we have on double precision or single precision computers, it runs into ill conditioning. If you want real speed, one should use half precision. But if you don't care what your answers are, if you're interested in speed versus garbage, then I recommend using half precision, even though your results are garbage. Garbage in, garbage out. That's what we say in the United States. Okay, next slide. So brute force discretization is a throwback to mesh-based schemes like finite difference, finite elements, or finite volumes. High gradient regions require extremely fine mesh spacing, and coarser regions, flatter regions, can use a coarse spacing. So the local length scale is really proportional to the absolute value of the function over its gradient. And pardon? Okay. And okay, so I just want to point out that when you take a look at, say, when the gradient is very flat, that means the gradient of the function is going to 0. So you can use a very large length scale. The gradient is very steep, then you need to use a very fine spatial scale. So you can use this sensing and the function, whether it's known or unknown, to get your level of refinement. Okay, next slide, please. Okay, now domain decomposition is a divide and conquer scheme, and it's one of the most more or less standard books is that of Smith, Burstead, and Grope. And I want to point out that these schemes are iterative. They are not exactly they're not exact, because when you try to solve things iteratively, it could converge. You're not ensured convergence until you go to an infinite number of um, um, processes. So basically we know that smaller problems are better conditioned, and non-overlapping yields higher continuity. So parallelization was demonstrated by Igber and all for radial basis functions in 3D. Next slide. Now, I showed previously what the basis function is. It's also influenced by the shape parameters C sub j or the exponent. So basically you'd like to have the basis function to be flat near the data center. So you can do this by either increasing the exponent beta, or the increasing the shape parameter. So going either way, increasing the shape parameter or increasing the exponent makes the basis function flatter. Next slide. So here's, see, I have several basis functions here. The dotted lines show the basis function with a small, excuse me, with a small shape beta 1/2 and a small shape parameter C. And the one on the top, the dashed lines, is beta with, dotted lines are, I'm sorry, it's 3/2. I have a misprint here. It should be 3/2. So it's very flat at the data center, and notice at the ends it really rises rapidly. So you could get flatness by increasing the shape parameter or the exponent. Yeah, I should have checked that. Sorry about that.
It's okay.
That's a misprint. Okay, next slide, please. So just showing you various things you can do. Now, finite elements relies on preconditioners for large scale simulations. So even though finite difference, finite element, finite volumes have compact support, when you have huge systems equations, they also become very ill conditioned. So this thing about ill conditioning is really a condition of round off error, nothing really intrinsic about whether you use continuously differentiable radial basis functions, or if you use compactly supported radial basis functions, or whatever. So I'm going to have, I will send you a paper that a presentation that I gave with the boundary element presentation 44, showing that you have using a combination of block Gaussian elimination and uh, extended arithmetic precision can bypass this, and you can get extremely good answers with something really nasty like the van der Monde equations. I did 144 van der Monde equations. The condition number of that was 300 to 310 to the 313.
Wow.
And the yeah, I
And
did
it's
this
so
on
good.
my laptop. Yes, and the answers convergence tested the convergence. The answers were good to 10 to the minus 92. So it's a combination of block splitting. So the thing is, the smaller the block sizes, the less the conditioning number is, and you need extended precision. Like I said, you could really zip through this if you want half precision, but if you want to just uh, uh, do pointless exercises, then use half precision. But if you want some real scientific stuff, you need extended precision. Okay, and I use Advantix. So yes, my cohort in crime is Pavel Horoborko. Okay, next slide. So, like I said, the C scheme where you increase the shape parameter is computationally efficient. Anyway, with this, you can use 100 to 1,000 times less resolution. And with the new process that I just showed at BEM44, you could even do better. So the thing is, you can't use single or double precision if you want to do this. So the thing you probably heard is there's no free lunches. So if you want good accuracy, minimum number of computational work, you're going to need extended precision and block conditioning. If you want a real fast but garbage work, then use half precision. So, like I say, you got to pay something
Definitely.
for your time. But I'd rather err on the order of accuracy. Now, for instance, if you know, there's a guy named Alain Kassab and Eduardo Diva who are doing arterial stents for people who have blood clots and so on. So you want very high accuracy when you dealing with human beings. Now so you need this precision. If you're doing some real crude engineering estimates, maybe back of an envelope, so you don't need that. So it depends on what your application is. Next slide, please. Okay, Neumann boundary conditions tend to have a loss of accuracy at the boundary. And this comes back to Modich's estimate, where you have lambda nu to minus gamma, where every time you take a derivative, you are losing your accuracy. So one way to do this is to increase mu, which is the ratio of H over, no, C, the C parameter over the mesh spacing. So you can increase the shape exponents C and or decrease the spacing between points. So it's cheaper to do it by increasing the shape parameter. Next slide. Okay, so I'm going to give a solid mechanics problem. This is from Timoshenko, where we have the displacements. I'm just giving the formulation. Sure, guys who are doing anything in civil engineering are familiar with Timoshenko and Goodyear. So we have anyway using the Young's modulus of 1,000, Poisson ratio of a third. L is a half. L is 12. The diameter is 4, and I is the moment of inertia, and P is the applied force. Next slide. So anyway, we're looking at the stresses, the shear stresses. So here we use the shape parameter of 3 and 10. Notice that we have big reductions in the error in the shear stresses. When we look at the log of the of the spacing between points. So the finer you make it, the better the convergence rates are. And also you see the difference between a small shape parameter and larger shape parameter. Next slide. Okay, these are the root mean square errors with different solvers. So we're looking at Neumann boundary conditions and Dirichlet conditions. Now, of course, you would assume that the Dirichlet conditions would be more accurate because you're not taking, you're not imposing gradient conditions on the boundaries. So we can see, for instance, with the displacement in U of X, that the Dirichlet is about 100 times better than the Neumann boundary condition. Same thing with the displacement in the y direction. The also you have good good errors with using the compression stresses, and also it depends on the solver too. So if you use Dirichlet on the compression stresses, you see a 100-fold, almost 100-fold, 50-fold improvement in the estimates. Next slide. Anyway, this is dependency of the L2 errors on the shape parameter. And this is with various, so I'm taking displacements in the U and X directions, and also in the shear stresses. So you can see here with different solvers, the Gaussian elimination, singular value decomposition, that we get very good improvements in the errors in things like shear stress and displacements. Next slide. So this is the shear stress on the midsection of this Timoshenko beam. And again, the solid line is the exact solution. Then we have some of the better results with the triangles are the extended precision. And here you can see that they fall right on the curve, whereas the crosses of the circles and the X's are rather high, and again they have these. They also have a dependency on the shape parameters. So next slide. So the optimal is for this particular case is 6. So here we look at the error distribution in the stress field, the scatter dated interpolation. The top figure A is with adaptive mesh refinement, and B is with adaptive shape parameter refinement. Now, notice that at the boundary, just doing some refinement on the distances still leaves errors on the boundaries. You can see they're rather high, but notice when you do the refinement on the shape parameter itself, you just have very little at the far corner. So increasing, dealing with optimizing the shape parameter has a nice effect on really minimizing the errors in the so anyway, that's what I wanted to show you. You could play games with this, and you can see the effects of tuning either the spacing H or the shape parameter. Anyway, the Professor Chang wrote a nice paper on this also.
Yes.
Thank you. Next slide. Okay, so this is Wang et al. And engineering analysis boundary conditions. They looked at double and quadruple precision for a CNH scheme. So fix the CNH, the quadruple precision requires is about 50 times longer in execution time than the double precision. So, and I should put down what the half precision is, but I didn't bother because the answers are nonsense. Anyway, if you looked at the time for refining the shape parameter in quadruple precision, that time is 1/565 that of the double precision scheme. The thing is, the reason that if I look at each operation in quadruple precision, of course, it takes longer. But the thing is, the total time is decreased by an order of 565. So again, you got to pay, no free lunches. Excuse me.
It's okay.
So if you have better precision, the total time can be reduced significantly, and this is kind of outdated. I can do better than this with the latest scheme I have shown. Next slide. So the answer is, how accurate do you want to look at? Next. Okay. The accuracy of the multi-quadratic scheme is impossible to meet by finite elements or finite difference methods. And the reason is it's just the time that you need. If you look at just what it takes to solve one operation in finite elements or finite difference, it's very small. The thing is, it takes so many more operations to do this. So anyway, this is something that was found, got an accuracy of 10 to the minus 16 by using a 20 by 20 grid in the example. Next slide. Next one. So assume, and this is I'm stealing from Wong and also Alex Chang. So if you want the finite element or finite difference model to solve with an accuracy of 1%, you're going to need to use quadratic elements or central differences and get an estimate of the shape parameter h squared. To reach this accuracy of 10 to the minus 16, h needs to be refined 10 million fold. So that so in a 3D problem, 10 to the 7-fold means 10 to the 21st fold in degrees of freedom. And your matrices will need to be 10 to the 42 elements. And then you would take this cubed number of operations, be 10 to the 63 fold. So anyway, if the original CPU time is 10 to the 100th of a second, so you'd need 10 to the 54 years. Anyway, the age of the universe is only 10 to the 13 years.
So we spend another age for the universe to solve one problem.
Yes. Okay. All right. So next. Anyway, something was also looked at by Fornberg and Zhu. And they looked at this thing of the shape parameter. And they found that you could get some improvement with the shape, with the variable shape parameters, decreasing the error and run times a little bit. Next. On the boundaries, the PD exists every place over the whole all the universe, but the boundary conditions make the problem unique if the problem is well posed. So the thing is, we can add points on the boundary can be slightly outside of the domain omega. Next slide. So implementation is that we have the multi-quadratic shape basis function like ck to the beta. Now beta is going to be minus 1/2 or greater. So we Wirtz, Kansa, and Ling show that with beta equals 5/2, this makes it the multi-quadratic parameter basis function look like a higher order monotonic spline. And the thing is, we also let on the boundary the shape parameter to be 200 times greater than that of the interior. Next. So using an equidistributed set of data centers is efficient and accurate for Neumann boundary conditions. Now, if you specify, say, the temperature gradient on the boundary, it can be accurate if the centers are both inside and outside, and even though they're widely separated. So this is, how you can worry about getting good Neumann boundary conditions. Okay, next. Fedoseev et al. Used extended the PDE boundary to be slightly outside the boundaries, and observed exponential convergence at the elliptical PDEs. Next slide. Okay, so I just want to show you these stars. The red line is the boundary, and this is, say, the domain omega. Anyway, you can have some centers slightly outside the domain, and it improves the results, especially for Neumann boundary conditions. Next slide. So this is a trick we use. You don't. No. Oh, the heck. The next slide. I had this already. Oh, okay. So anyway, what the Wirtz study showed, if you had that exponential greater than 1/2, produces rapid convergence. The boundary conditions on the PD are unique, assuming well-posedness. And then you could let the boundary conditions, the shape parameters on the boundary be much greater than that of the interior. And so if you permit the shape parameters on the boundary and the interior to be different and tossily, you can reduce the RMS errors even more and get better conditioning. Next slide. So another thing with meshes is you can do front tracking very simply. You don't have any complicated mesh divisions, getting smaller and smaller as, say, well, think of it this way. I can form a discontinuity by having those speeds, the characteristic speeds, convergent eventually in time. So what I do is I can always tell when the when the points are going to coalesce to form a discontinuity. And that's very simple when you're using hyperbolic methods. So I don't need to use artificial surface tension and viscosity and all this other non-physical stuff to change the physics. I'll just tell you, I am a physicist, and to me, I think using all these numerical tricks is just well, very disturbing to me as a physicist that you change you change the physics to suit the numerical scheme. You're supposed to change the numerical scheme to suit the physics. Physics is more important than numerics. Okay, next. So what I did was looked at Sethian's test of a cosine front. This is supposed to be a simulation of say, a flame front in which the flame is a cosine function separating burnt and unburned gases. The front should develop a sharp cusp in the direction of the normal velocity. And conversely, a front should flatten if the front faces the opposite direction. So the flame is moving only by jump conditions in the local normal direction. This is flame fronts and shock waves are kind of similar in this respect, that they only move by the Rankine-Hugoniot jump conditions. Next slide. I'm getting a message. My internet connection is unstable, so I just want to let you know, guys, about this. Okay.
It's okay.
So front tracking requires lots of physical viscosity. It's it's just gross what some people have done with shock waves and so on. So they make it too complicated, like keep on dividing and moving things in time. I like William of Ockham's recipe. He was a English monk in the 11th century. He said that the most correct approach is the simplest approach. In the United States, the approach they also you say is the KISS method: keep it simple, stupid. So the simple approach is usually the best approach. That's what William of Ockham said, and that's what some people in the United States say: keep it simple, stupid. So especially when you're doing numerical mathematics, doing it simply is best, is usually the best approach. Next slide. Now, maybe some people are going to find this offensive to me. I get the best approach with a variable shape parameter, c squared. Kind of goes like this, linear. Sometimes it goes quadratically, so on, or exponentially. Next slide. Oh yeah, this does go exponentially. Sorry. Okay, here is the Sethian thing that you have the flame front, and you can hear it's discretized here. So as it advances, you're going to see it sharpen. Next slide. Oh, it flattens. It flattens this way. Next slide. Okay, this is going in opposite. This will sharpen, form a cusp. Next slide. Okay, notice how sharp it gets. So yeah, I had, sorry, I got the two curves mixed up. So in one case, when you're going in, so in the direction of the propagation, you find that the front sharpens. Next slide, please. Okay, this is with 2D vortical combustion. You have infinitely periodic turbulent flame, and So I have where this is. It's in engineering analysis with boundary elements, volume 31. Now the flame front is discontinuous with the flame spread. And so it's burnt and unburned gases. And this flame is going to start out flat. And because of the flow is turbulent, vortical flow, it's going to look sinusoidal. Then after some more time, it'll flatten. Then after some more time, it'll look sinusoidal. It keeps on going infinitely long. And since there's no numerical dissipation, it gets boring. It looks flattens, becomes very curved, flattens, very curved. Okay, next slide. So like I said, it starts out very flat. And because of the vortices, next slide. As you can see, it's beginning to curve. Next slide. Curves more. Next slide. It'll start to flatten. Next slide. Okay, didn't rank quite now. Next slide. Begins to flatten. Oh well, I got more in the paper. So okay, I just want to show that if you want to do this, the traditional finite difference method requires 14 hours on a parallel computer to get a goal time of 1. The time required for the radial basis function method to reach the time 1 was 23 seconds on a PC. So we don't need all that. So got some summary. So the thing is, you can use spatial refinement sparingly. The shape parameter is basically, can vary with the curvature, the radius of curvature. And when you want IT singular value decomposition, means you have small singular values into the null space. Anyway, you can show when you use higher precision, quadratic precision, it is cost effective in reducing the total CPU time. So domain decomposition, preconditioning, and extended precision need to be examined. Anyway, I can send you the some of the write-ups that I have done with
Yes, please.
Professor Chang to show you the new approach that you can use extended precision and block Gaussian elimination and get some really nasty problems done with I mean, the fact that I could do a von Neumann equation with 10 to the 313 condition number and have RMS errors of 10 to the 92 minus 92 means it's a good approach. So we need to think beyond the box. Okay. So any questions by anybody?
No, I think there
Questions,
is
comments?
something in the chat room. I think I'm trying to. How can I do this?
Do you want me to speak? Do you want me to speak to put that question? Or?
Yes. Go ahead, Daniel.
Yeah. Okay. Yes. Very interesting talk. Thank you very much. It's been a pleasure. I just have a question related to practical data. Any boundary data that we may prescribe as a boundary condition comes in fact from experiments, and these are subjected to what we call random noise. And this experimental noise with which we have to live with as engineers or practitioners then is much bigger than any numerical round-off computer precision error, which you have discussed about. So in that case, I think it's more difficult probably to choose these multiple shape factors or something.
Uh-huh. Yeah. You probably, I haven't done that much with experimental data. One who has done it is Benny Han in Hong Kong and Li Van Ling. So I would recommend contacting them. I think they were working with some Japanese company with dealing with furnace temperatures, and I think they can help you with some real practical advice. So yes, you need to do two things. You need to worry about the numerical inaccuracies,
Yeah.
and also the computational things. The thing is, I would rather minimize the numerical noise and then concentrate on the experimental.
Yeah.
When you're trying to do both of them together, you're mixing the two, and it's hard to separate out what is going on.
Yeah.
So I recommend contacting them.
Yeah. No, thank you.
Leave on Ling. Yeah. Okay. Oh, okay.
Professor Kansa, for this nice talk. I don't know whether there is other guys have a questions. I have a very simple question. When you extend the points beyond the domain omega, what kind of boundary conditions you put?
I think these were used for Neumann boundary conditions.
The same boundary conditions, you mean?
Yeah.
Okay, I see. Okay.
So for both, but it's most effective for Neumann boundary conditions.
Okay. Actually, most of your talk confirmed the talk of Professor Chang before you direct. So placing the two talks after each other was great, to be honest.
Okay.
Okay. Thank you, everybody. I don't think there is other things to other question. Do you have any closing word, Professor Kansa, or something like that? Professor Chang, do you have any closing word or anything?
No, just thank you for organizing this nice scheduling. So
Thank you.
Yeah.
Thank you. So by this, our day will be ended. Tomorrow morning, we will start a very big lecture about our software, our developed boundary element-based software. This lecture will be about 2 hours or something like that. We will see that boundary elements can be put in practice. We can solve real tall buildings over soil, including soil structure interaction and nonlinear soil structure interaction. After that, Professor Xinghua Xin will give us some talk about Crafties and finite and the fundamental solution-based finite element, and we will.
Okay.
Okay.
Sorry.
Okay.
It is internet interruption. I'm sorry. So after that, we'll end up our talk tomorrow by showing a method we developed here on modeling nonlinear applications with boundary elements using HLP inclusions. I will be happy to have all of you tomorrow. And from now to tomorrow, we'll see you all. And thank you. And I'm really happy every day. I'm really happy to have some good words about boundary elements and computational mechanics. Thank you, Professor Kansa. Thank you, Professor Chang. Thank you, everybody, for attending with us. Thank you.
Thank you. Bye-bye.
Okay, you're welcome.
Bye.
Goodbye. Bye.